Hi everyone, welcome back. Today I want to walk you through a paper that I think is genuinely worth your attention. It's called VoxCPM, a tokenizer-free text-to-speech model from OpenBMB. Now, if you've been following the TTS space, you know that there's a long-standing trade-off that no one has really cracked cleanly. And this paper takes a pretty elegant shot at it. So let me set out the problem first. When you're building a TTS system, you basically have two passes. Pass 1, you tokenize speech into discrete units, like how we tokenize text. This gives you stability. The model knows exactly what to predict. But here's a catch. You lose acoustic detail. The quantization process threw away subtle information, things like brightness, micro variations in pitch. The output sounds clean, but not alive. Pass 2. You go fully continuous, predict raw acoustic features directly. This preserves all the richness, but now you have a different problem. Error accumulation. Small mistakes compound over time. Long sentences start to drift. The model loses coherence. So, the field has been stuck in this dilemma: stability or expressivity. Pick one. Now, here's where VoxCPM gets interesting. Their key insight is you don't have to choose. What if you could separate the two tasks, semantic planning and acoustic rendering, within a single end-to-end system? Think of this way. When humans speak, there's a high-level plan. What to say, the prosodic, the rhythm, and then there's low-level execution. The actual timbre, the fine acoustic texture. These are different cognitive processes. VoxCPM mirrors this separation architecturally. They introduce what they called a semi-discrete bottleneck, a finite scalar quantization layer, or FSQ. This sits between the semantic model and the acoustic model. The FSQ acts like a checkpoint. It forces the first model to focus on high-level structure, content, intonation patterns, because only that information can pass through the bottleneck. Then a second model, the residual acoustic language model, fills in fine details that got filtered out. Let me break down the architecture quickly. You have four main components. 1. The semantic language model, or TSLM. This is initialized from a pre-trained LLM, specifically Mini CPM4. It takes in text and generates semantic prosodic representations. Essentially, it's planning what to say and how to say it at a high level. 2. The FSQ bottleneck. This quantizes the TSLM output into a semi-discrete space. It's not fully discrete like a codebook. They use 256 dimensions with 9 scalar levels. Enough structure to stabilize, but not so restrictive that you lose information. 3. The residual acoustic language model, or RALM. This takes the quantized representation and edits back the acoustic details, speaker identity, spectral fine structure, microprosodic variations. 4. The local diffusion transformer. This generates the final audio latent through a diffusion process, conditioned on the combined output of TSLM and RALM. The key point, the whole thing is trended end-to-end with a single diffusion objective. No separate pretrend of tokenizer, no fragmented pipeline. Alright, so does it actually work? Short answer, yes. Impressively so. On the SEED-TTS benchmark, VoxCPM hits 1.85% word error rate for English, 0.93% character error rate for Chinese. This is state-of-the-art among open source models. Speaker similarity scores are also strong, 72.9 for English, 77.2% for Chinese. And critically, it handles hard cases well. The error rate on challenging sentences is significantly lower than comparable sentences. That is exactly what you'd expect if the bottleneck is doing its job, preventing the kind of error accumulation that kills long-form synthesis. Now, my take on this paper. I'm cautiously optimistic. The architectural insight feels right. Separated semantic planning from acoustic rendering is a principled approach. The ablation studies are true. They actually show that removing the FSQ bottleneck causes performance to degrade, especially on hard cases. That says, there are limitations. It's bilingual only, Chinese and English. The audio is 16,000 Hz, which is below production quality for many applications. And the fine-grained control, like explicit emotional or speaking rate, isn't addressed. But as a research direction, I think it is the right track. Alright, that's VoxCPM. If you want to try it yourself, they will release the code and the model weights under Apache 2.0 license. Links are in the description. Thanks for listening. See you in the next one.